Hi, and welcome to the first Duality AI webinar um, uh, that we're doing. It's really glad to have you guys all here. Thank you for joining us. Before we kick off our today's main topic, I just wanted to uh, introduce sort of just a few real quick points. So, uh, okay, apologies. This is at our first time, so figuring out a few small bugs here. All right. So as mentioned, today's webinar is called Using Synthetic Data to Train AI Vision Models. And here with me, I have Gandharv Mahajan, our solutions architect, and Felipe Mejia, who is a AI vision engineer here at Duality. And they're going to be talking to you about how we use synthetic data and sort of the lessons we've learned along the way in using it to train AI. In terms of the topics that they will cover, a lot of the concepts will come up are actually covered in our recently debuted EDU tier of Falcon. And you can actually see a lot of how this works by trying out our collab example. You can find the links in the description of this video and in the live chat as well. But you can go through the whole exercise and see it for yourself directly in your browser. The way today's webinar is going to go is Gandharv will first talk about generally what Duality does and some of our use cases with synthetic data. And then Felipe will go much deeper into how we use it, how we create it, and the frameworks that we have with thinking about it and working with it. At the end, we've saved some time for questions. Thank you, everyone who sent those questions in ahead of this event. We'll try to get to as many of them as we can. Please feel free to also add questions in the live chat. If we do not get to any of your questions, we will address them all on our Discord server, and you can find a link for that in the comments, in the description below as well. And with that, I'm going to hand it over to Gandharv.
We'll share my screen. So hello, everyone. My name is Gandharv Mahajan. I'm working as a solutions architect here at Duality. Been here for about 2 years now, about in March. My background is in robotics, mechatronics, did some AI work in the past, sprinkled all over. So with that, let's get started. So Duality comes from two co-founders, one coming from Caterpillar, the other from Pixar. And really the founding question was, how can we use tools from the entertainment world to solve some of the real engineering problems like robotics and AI? So maybe before we get started, let's talk about some of the problems we are tackling here at Duality. First, AI models require a large amount of data, which might not be easy to source all the time. So for example, if you look at the image on the right, if you want to train a self-driving vehicle to drive on a road, you would ideally need data sets ranging from all sorts of diverse conditions. Maybe you want a cloudy sky, maybe sky with some lightning, maybe a wet ground. Now, to get those images in the real world, it's very hard to actually go in and create those. So we need a virtual system like Falcon to create those. The second problem we are trying to tackle is AI and robotic systems must go through multiple iterations before they come to reality. So ideally, we would want a virtual environment to train and test these robotic systems before they ever come to reality, even before like any hardware is ever deployed in the real world. So the solution we have here at Duality is in two folds. The first one is open loop synthetic data generation. So again, if you look at the videos on the right, if you want to create a data set of test tubes for a pick and place operation through this robot, you can't easily create that in the real world, but you can use a system like Falcon to generate multiple images for this kind of data set in different kinds of modality. Although in this case, you see only RGB images, but you can get images from the thermal sensor. You can create LiDAR signature. You can do that in the GPS IMU band as well. And the second solution is closed loop policy training and testing. So, for example, if you have a quadruped robot, you can put them through diverse conditions. Again, the problem here is all these conditions might not be easy to access in the real world. But in a virtual world, you can just put your quadruped through a forest environment, an icy land, or a desert, and train these intelligent policies through RL. Um, so let's talk about some of the customer use cases we have solved in the past. First one being defect detection on high-speed manufacturing lines. So our manufacturing customer needed to demonstrate a 99.95% accuracy rate in detecting minor imperfections. 2 years of training with real-world data, accuracy stalled at 96%. But 4 months of synthetic data training through Falcon, we could deliver an accuracy of 99.98%, which is a pretty large boost. Now, if you imagine if you're creating 10,000 imperfect objects a day, you would just miss 9,600 those objects, which is pretty high. Even though 96% sounds a lot, it is not a lot on a high speed manufacturing line. Uh, Second use case is virtual training and testing on off-road autonomy. One of our other customers needed an efficient way to collect data and develop autonomy. So we showed that with Falcon, we can generate off-road scenarios and vehicles under diverse conditions scalably. At the end, the results were that we were able to produce 10% and more accurate perception models in unseen environments. So, for example, if you are training uh, your off-road autonomy stack in just forest in the real world, but in the virtual world, if you're training those in forest environment, in icy environments, in desert environments, uh, the sim to real gap when you just transfer your autonomy stack in the real world on a desert environment, it's pretty low. So with that, I'll uh, transfer it to Felipe. Stop sharing.
Yeah, thanks for that. So thanks again, everyone, for joining us. I think definitely this is a super interesting topic, especially as part of machine learning. I kind of think of it as like there's three main parts to machine learning. It's basically like the hardware, the algorithms, and then the data. And so being able to use synthetic data is really a crucial part to developing good AI models. So I'm happy to have all of you guys joining us today. And so again, I'm a machine learning engineer at Duality. Been working here for over 3 years and basically working on both how can we use machine learning models internally to improve our processes, as well as more of like, what are the best ways to use synthetic data to train machine learning models, which is part of what we're mainly going to be talking about today. And so hopefully by now, with Gandharv's great talk, you've sort of understand the promise of synthetic data, which is to build scalable, cost-effective, adaptable, and easy to label AI. Basically, synthetic data, the labeling costs are almost free. You basically, especially with Falcon, you can just create your data set and just get different variations of annotations at the push of a button. So we're really trying to, so synthetic data really has a lot of that promise. And if we kind of dive into kind of the adaptability of synthetic data, you can see kind of examples here where we have a vehicle in a desert environment, or we can have a vehicle in the moon. And these are sort of data sets that are very drastically different. Obviously, getting a data set of the moon is very challenging and difficult, and can, for the most part, only be done in simulation. And so that's a great strength of synthetic data, but that also is one of the challenges to synthetic data, in that we have all of these infinite possibilities of environments and worlds that we can generate, but there's only a very limited amount of realistic, high quality synthetic data that will actually lead to a machine learning model that performs well when it's deployed in the real world. And so there's a lot of ways to make bad synthetic data, and there's a few ways to make good, high quality synthetic data. And so, and it's not easy to sort of create the synthetic data. And basically, there's a lot of complexes in the real world that we really need to capture. And so there's historically some stories of synthetic data kind of frequently falling short for customers. And to really unlock the potential of high synthetic data, we really have to ensure that our synthetic data is real and has that realism aspect, and also has diversity, is not just kind of redundant, and captures a lot of various different forms of data that will lead to a model that performs better. And so really to avoid sort of these shortfalls and these issues, at Duality, we developed basically a systematic approach to evaluate the realism and diversity of our synthetic data. Basically, we call this the 3I framework, which is basically a systematic approach to provide quantitative measures of what is our synthetic data realistic enough? Is our synthetic data diverse enough to create models that will actually be robust and work well in the real world? And so diving into what this 3I framework is, we basically have three components to it. First is indistinguishability. And so indistinguishability is really about, can we generate synthetic data that a machine learning model can differentiate from the real world data? So this is the realism aspect of how can we basically develop a machine learning model that, develop a synthetic data that from the point of view of a model is exactly the same or indistinguishable from the real data. And so this is basically, if we have, we want to be able to provide synthetic data that is given to a machine learning model, it's trained on that. And once it's deployed to the real world, there's no actual difference. And the model is basically seeing the same thing that it was trained on. It's seeing the same thing that it's seen in simulation. So we want to kind of minimize that difference so that there's a smooth transition from training on synthetic to deploying on the real world. The second I is information richness. And this is basically about the ability to not just recreate real data, but really be able to expand on our sample, our real data sample. We want to generate new perspectives, new angles, new possibilities that weren't necessarily captured in the small sample of real data, and that we can possibly oversample or increase if there's some challenges there. It's all about providing new perspectives. And finally, there's intentionality. And this is basically, how do we define what we're interested in? How do we define our use case, our domain of interest? How do we define what we're really looking for in our data set, and what we're looking for in our what we're looking for our model to learn and be able to use as it's deployed into the real world. And so let's dive into the 3I's a little bit more. First, indistinguishability. And so again, the idea is that we want to make sure that our synthetic data and our real data are as indistinguishable as possible. There's a lot of different synthetic data that can be generated. You can have, going back to, hopefully you've seen the EDU examples, exercise 1, where we work a lot with the Cheerios box. If not, feel free to check that out and go to that link. But basically, you can have something where we have a digital twin of a Cheerios that doesn't look very realistic, or we can have something, a digital twin of a Cheerios that looks more realistic. And so we really want to get into a space where both the real and the synthetic data meet and be able to create a synthetic data that is matching that real world data set. And so we really want to start by having could be something as small as one image or a larger data set of real data, and use that to really be our target of what our synthetic data wants to look like. We want to have a way to ground our synthetic data with real data so that we know that our first step is matching that realism through indistinguishability. And so the way we provide a metric for indistinguishability is that we basically process the data sets that we have available, both synthetic and real. We process them through a computer vision model. For the most part, we tend to use DynoV2 because of its general properties with being able to be used for a wide range of different use cases. And so we use DynoV to process the images and extract embeddings from these images, and then do dimensionality reduction on those embeddings to convert images into basically 2D coordinates. So in these two scatter plots, each one of the data points here represents a image. So the red dots are images of real Cheerios boxes, and the blue dots are images of synthetic Cheerios boxes. And so here on the left, we basically have distinguishable, what we would call a distinguishable data set, because we basically have our red dots are all kind of clustered together, and our blue synthetic dots are all clustered together. So it's very easy to draw a border to distinguish between what is real data and what is synthetic data. And on the right, we're looking at something at a data set that's more indistinguishable. So you can already see by the two examples that we have, where the blue dots are synthetic, the red dots are real data. It's already hard to tell visually, and the machine learning model has a similar opinion or similar results, where basically we're getting these scatter plots that are basically scrambled together, and there's not really a clear boundary between the real data and the synthetic data. And so this is what we would consider a indistinguishable data set, because they're mixed together and scrambled without a clear cluster between the two. And so how do we turn this into a actual metric? The approach we took is basically we have these scatter plots, and we're basically looking at the statistics of how many times is the closest point to a real point synthetic, and how many times is it real. And basically for a simple case, when the two data sets are equal in size, we just multiply this times 2 and we get our indistinguishability value. So basically the idea is that if something is like completely randomly mixed together, that it should be equally likely that the nearest neighbor to a real point is a synthetic point versus another real point. And so that's basically the assumption that we do here, and we get an indistinguishability value. Definitely a lot of different forms that we can get this, but this has been what has worked pretty well for us so far. And so diving into how do you go from a distinguishable data set to a indistinguishable data set? Some examples of what has worked worked for us in the past includes matching the camera parameters. So one of the first things that we sort of suggest is to make sure that you understand the camera properties of the camera that you're using, whether it's just playing around with an iPhone and understanding and looking up what some of those camera properties are, even if some of them are harder to get, or you're using a more heavy-duty camera to capture your data set, or lots of different ways to capture images. you really want to understand what are some of the camera properties and collect those. And once you have those, fortunately, we have Falcon that provides an easy way to sort of use and leverage those settings and just plug them into the Falcon simulation to change the camera properties of the sensor that you're using to create the synthetic data. So we want to make sure our camera field of view is correct, our image pixels, also camera noise. Most cameras don't have a very thorough information about camera noise. So this is more of a exploration area where Falcon provides a way to add camera noise to the images and the synthetic data, and you can sort of modify that to best match your the real data that you have. And then finally, there's image format. If you're saving in JPEG, you want to make sure that your synthetic data is also JPEG if it has the same sort of compression level, and try to match that appropriately. So here's kind of some examples where the blur was originally on the top, the blur was originally off, and then we kind of improved the blurring parameters to create a more realistic data set. And then on the bottom, we had some image that had JPEG compression versus an image that doesn't have JPEG compression. And so this is something that's really can be absolutely crucial to kind of not as important. And it really depends on both the images that you have coming in as well as the machine learning model that you use. For example, if you have images coming in that are very high resolution, something like 4K or greater, and you have some of these blurs and some of these noises, and you're trying to process them through something like YOLO. YOLO, by default, will downscale those images to 620 or 640. And by doing that large downscale, it's kind of removing most of these noise artifacts. And so in that case, you don't really have to worry about it. But if you have images coming in that are closer to that 600 by 600 pixel range, and they have noise, then it becomes crucial to be able to capture all of these different noise properties effectively. And so the other thing that we've sort of seen some positive results with is making sure your labels are matching the labels of real data. So this is basically looking at, so here are two histograms basically looking at the image pixel size of an object in the data set. So this is basically looking at how much of the image is actually composed of the object of interest. So if we have some, and particularly these are coming from the exercise one for from the Falcon EDU. So again, these are looking at the Cheerios data set, both real Cheerios data set and synthetic Cheerios data set. And so what we can see is that there's, in our real data set, there's a lot of large images of our Cheerios box. And on our synthetic data set, there's not as many. Most of them are from far away, and the Cheerios box is actually smaller. And so what we've seen is that we really want to capture what the real data has. And so what we can do is that we can basically add some examples of the Cheerios box closer to the camera so that we have more of those images of the Cheerios box as a larger portion of the image. So that's the image on the right, where now we have synthetic images, some synthetic examples of the Cheerios box actually being larger and bigger. And so even this image on the right is not perfectly matching the real data, and that is sort of, we'll come back to that in intentionality, but that's part of why we have three eyes. And I'll talk about this again in a little bit, where indistinguishability is a big part and probably one of the biggest challenges to synthetic data, but there's more to it than just indistinguishability. And so that's why we don't match the real data perfectly for this. And so the other thing that we've done in the past is basically making sure that our color temperature and our colors match what the real world data is sort of telling us it should look like. So there's definitely a lot of really good methods for doing this. And this would be more of like a lot of work on machine learning and AI techniques, such as domain adaptation, with something like cyclogans being a popular and very interesting approach. What we've seen challenging with sort of this idea of training a machine learning model to basically make synthetic data look more realistic is that it requires, even though it doesn't require labels, it still requires a lot of real world data. And the data size is still very large. And in a lot of these cases, what we have is basically the access to real data that we have is very, very limited. And so we're not able to use some of those techniques as efficiently as they would require. We don't have basically the data requirements to really leverage some of those sophisticated techniques. Fortunately, what we can do is do something more basic that will get us 80 or 90% of the way there, which is basically just make sure that that our images are normalized to the same properties that we're seeing from the real data. So we want to make sure that if we calculate our mean and our variance of our synthetic data, and we match that mean and variance in our simulated data. So we want to make sure that we have these properties. And so again, this is something that we can do with the Cheerios boxes. And what we see is that basically the color temperature could benefit from increasing and making it a little bit warmer, as seen here. And so diving into, okay, so we have indistinguishability. What does it mean for our main goal, which is to make machine learning models that are that perform very well and are able to work really well when deployed in real world data. So what we did what we've done is basically kept track of the different digital twins and different use cases that we've used, that we worked on through some time at Duality. And we looked at the indistinguishability scores of these different models of these different synthetic data that we have, and compared to the overall model performance. And so although there's not like a perfect relationship between indistinguishability and model performance, there is definitely some relationship there. And again, this is it's not a one-to-one match, because again, this is one of the three eyes. There's definitely more to just indistinguishability. But we definitely observed that highly realistic and synthetic data can lead to higher performance in our mean average precision of models trained on that synthetic data. And so diving into the other eyes, because again, indistinguishability is kind of one of the main pieces. Indistinguishability kind of tells you whether you're matching your target real world data. But if our data is indistinguishable, but it doesn't provide new information, we're basically just creating redundant data. We're basically just either replicating the real world data, or just being very redundant and sort of creating the same data set over and over again. So we want to make sure that our data is not just indistinguishable, but also provides a high degree of information richness. And so the way we sort of think of information richness is that it's a measure of the novelty and uniqueness of the data set. So it's like, do we have, is our data set from different angles? different perspectives? Is there different objects? Is it capturing a high degree of variability? And so diving into the again, the EDU exercise 1, there were 2 phases to that exercise. First was, can we put a Cheerios box in a living room environment and just have the Cheerios box be in different angles at different perspectives. And then 2 was, what do we do? What happens when we add different other objects into that environment? And so this is a great example as far as information richness. So we have data that's very clustered together. And so on the left is basically the data from that first example of just a Cheerios box in a living room with without other objects. And so our data here is very clustered. It's very small, everything, not a lot of variability. And so to make information-rich data, we want to add that variability. So one way that we can do this is to basically add those different objects to the environment and create a wider domain, a bigger domain with more variability and more changes into this environment. And so going into the specific examples, you can see here that you have the original Cheerios box with just in the living room with no other things in there. And then we have the Cheerios box with all of the different items that are adding that information richness to this environment. And so in the same way that we did this with an indoor environment, we can also do this with an outdoor environment. So with Falcon, you have this possibility to really take advantage of that strength of synthetic data, which is that ability to create a wide range of different environments and provide a wide range of different information richness. And so here we have an outdoor environment where we can change the weather, we can change the cloud conditions, we can change the time of day, dust level, and all these different things to provide that information richness into, we can provide that information richness to sort of create a synthetic data that's more variable and create models that are better prepared for those variations. It's basically, synthetic data is basically data augmentation on steroids, because now you can have so many more parameters that you can modify and change. And so information richness is really about how can we provide a metric that tells us how well we're doing in that regard of creating variability in our data set. So moving on to intentionality. So intentionality is really about defining how we care about our domain of operation. So again, we've originally talked about how synthetic data can make basically an infinite amount of possibilities and scenarios and environments. And so it's how do we define what is our domain of interest? How do we define what we're actually interested in? And so, for example, here, we can talk about 2 different use cases. One is like, let's say you have a autonomous home robot and you ask it to go get Cheerios. It might not be as important for it to be able to distinguish between a giant-sized Cheerios and a small Cheerios box or a Honey Nut Cheerios box. It's just go get a Cheerios box and there's only one Cheerios box. So it doesn't matter. It doesn't need to differentiate. So you don't need that variability, and the model doesn't need to understand the fine detailed differences between these different Cheerios boxes. Alternatively, if we look at a grocery store environment, and here we're looking at something like a self-checkout, automatic self-checkout, here it does become crucial to see the differences between those three Cheerios boxes. Uh, there's a price difference between the three Cheerios boxes, which is crucial to be able to differentiate. So we need to be able to define a giant Cheerios box, which is different from a regular Cheerios box, which is different from a Honey Nut Cheerios box. And so the intentionality is really about like figuring out what that definition is and deciding what do we keep in our data, what do we emphasize in our data, and what do we prune and remove from our data. As well as this, it's basically important to have that balance between what information richness are you adding to the data set and how much are you tying and how much are you expanding on the indistinguishability of that real sample data set that you have, and figuring out where that balance lies to create the best models and the best data set. So diving into a intentionality case study. So we can look at, again, two examples. One is looking at a production line. And so in this production line of, we're going to say suitcases, we have a lot of suitcases coming through. There's not a lot of variability to them. And we're looking at identifying small details that are different, small defects that are different in this sort of production line. And so in this case, our indistinguishability has to be very high because we're looking at key differences that we have to differentiate. Alternatively, for sorting and shipping, here we're looking at a domain that's much larger. Basically, we can have suitcases coming from all over the world with a lot of variability. And so we have to make sure our model is prepared for that large variability. And so here, information richness is more important. And so we have to provide more of that information richness to cover a larger domain. Similarly, we can also look at two different use cases: detection versus segmentation. And detection is this idea of generating a bounding box around the objects of interest. And here, synthetic data is a little bit easier for synthetic data to really shine. Synthetic data is basically more effective because you just need to create a bounding box, and you don't care about the specific boundaries, and that really provides you with more leeway so that the synthetic data just needs to be moderately realistic. For segmentation, you actually need to know the pixel level difference. And so this means that we have a higher demand of precise, realistic textures, lighting, to really be able to capture the object boundaries and not lose that distinction. And so finally, going back to that earlier example of object size, we have the main reason we don't dive into matching the real data perfectly is because our model, and for the most part generally, objects that are small are much harder. There's less features to basically find in smaller objects, and that makes it more challenging for the machine learning model to learn. And so although real data doesn't have as many small examples, these can kind of be considered more outliers. Because they're more challenging, we actually want to increase them in a synthetic data set because we can. And so here our data set's actually increasing the amount of small objects because of intentionality, because we're trying to upsample those kind of outlier and rare examples because they're challenging for a machine learning model. And so with that, I think we can jump over to questions.
Awesome. Thank you so much, Felipe. I mean, it's a fascinating topic and it is a lot of information, but it is so cool to see that there is really a very structured way to think about synthetic data and how appropriate it is, how useful it is to any particular problem. I will say, if for anyone who wants to also dive a little bit deeper into what Felipe was talking about, we're dropping a link into the live chat with our blog that we wrote actually about how the three eyes framework really works and the ideas underpinning that. So let's dive into some of our questions that were submitted. So the first one I have here is, and this is both to Felipe, both you and Gandharv. Please jump in as you guys have stuff to add. And that question is, can the training data be completely synthetic, or is it better to mix it with the real data? Is there a proportion that you're going for that kind of scenario?
I think for the most part, if you have real data available, it's always good to use it. For the most part, we haven't seen any particular case where combining the two was detrimental. We've seen some cases where using real data with synthetic data, the synthetic data is so good that the real data doesn't add anything. But for the most part, you can basically, if you have it available, you can mix it and add it in there to get the best results.
Got it. Okay, very cool. But there isn't like, so you don't follow like a rule where you're like, man, 30% this, 70% that. It seems it's really kind of case dependent on what your real data is.
Yeah.
Okay.
I think in some cases when real data is not available at all, like for example with the case on the moon, where it's just hard to go and collect some real data, we have to rely on synthetic data. So in that case, it'll be just 100% synthetic data.
Awesome. Okay, got it. All right. Our next question here is are there situations when synthetic data is not helpful or actually maybe hinders your AI model training? Is there cases where synthetic data is a problem where you really want to rely on real data that you guys have come across in your work?
Yeah, I think synthetic data is just, for the most part, it's so versatile. There's not really a use case where it's been detrimental. It really comes down to making sure it's well made. And so there's a lot of ways to make bad synthetic data. There's a lot of ways to make synthetic data that's like that does hinder an AI model training, that does actually like make it worse. But if you make synthetic data that's grounded on real world data that is diverse, it for the most part tends to benefit the AI model training. So I think because of it's kind of the two-edged sword. It's like there's a lot of benefits to synthetic data because of its ability and versatility. And that also means there's a lot of weaknesses because you can make bad data very easily.
Mm-hmm. Is there ways that you go about? I know you talked obviously in your presentation about, hey, this is how we ascertain how indistinguishable, how information rich it is, and we want to do this with intentionality, so we understand what is using that data, how it's using that data. Is there a way you go about judging the quality otherwise, or is it just an iterative process where you're like still trying to figure out what results did this data produce?
Yeah, I think definitely it's like an iterative process. And so a lot of the digital twins that we make, it's kind of like a process of making a digital twin, sort of making sure it's indistinguishable, adding it to the catalog once it's been validated, creating a scenario, making sure that scenario is indistinguishable, and then moving through that process to make sure that at every step of the process, we're making data that doesn't fall for some of those shortcomings and some of those issues. So it's definitely important to have that systematic approach so that at the end of the day, you make data that's realistic. Because if you go through the process and at the end you're trying to fix things backwards, it's so hard to know where the error is coming from. It's so hard to be able to like have this entire environment and I'm like, I don't know if it's the bookcase that's wrong, or I don't know if it's the couch that's wrong, or the TV, or there's so many components to it. So being able to systematically go through that process, I think helps with creating the best synthetic data we can.
That makes sense. Okay, our question number 3 here, and you may have covered some of it already a little bit, but how does the process of generating and integrating synthetic data differ for various types of AI vision tasks, like object detection, segmentation, pose estimation, etc.? Is it different, or is it kind of the same approach for all the different AI type of tasks?
Yes, I think so. What we've seen is that different tasks have a different degree of difficulty for synthetic data. So the easiest one is segmentation requires much more realism than detection. And so this is basically because for detection, you have a bounding box. You're trying to differentiate just a bounding box versus background. And so it's okay for the boundaries to be sort of blurry as far as like the model being like, okay, I'm not sure where the boundary of this object is. It's like you're just making a box. But for segmentation, you're comparing each pixel, and the pixels at a boundary are very blurry from the point of view of a model deciding whether it's a Cheerios or background. So basically, if the pixels right next to a Cheerios are very similar to the pixels next to a Cheerios, and so being able to differentiate those two is very challenging. And so if we make the problem harder, that means that our synthetic data has less room for error. Basically, the differences in the boundaries make it so that we have to make more realistic data. And so that makes it harder for synthetic data. Definitely doable. It just makes our work and our methods have to raise them to a higher standard.
I think post-processing could also differ a little bit when we go from just detection to segmentation. In detection, making things indistinguishable is slightly more important than making things more intentional or just adding background clutter in the case of segmentation. So it also like depends from use case to use case and what kind of synthetic data you're finally wanting.
Okay, awesome. See, question number 4. How do you ensure that synthetic data accurately presents your edge cases, like the diversity that you're looking for any real world scenario? Like how do you know that what you've done actually covers those cases that you really need for good performance in the real world?
I think some of it boils down to what Felipe just presented, the 3 I's. But it's also crucial to know that synthetic data at the end of the day, it's not a magic button. Because our synthetic data is coming from digital twins, like the underlying truth is digital twins. You have to have really high quality digital twins and really high quality simulation as well. So for example, even if you have high quality digital twins, but simulation is not grounded in reality, you can make bad synthetic data.
So in a way, you're saying if your digital twins have behaviors and properties that are very, very grounded in, as you said, in reality, or reflective of what would happen in their world, you expect that the edge cases you care about will get covered. Like they will produce those behaviors, they will produce those results.
Exactly.
Okay, got it. Let's see. Next question we have is, what are some challenges of getting started with synthetic data like this? I think Gandharv, probably especially in your work, you come up with this a lot, and I'm curious if you guys have thoughts on this. What are some of those difficulties or hurdles that folks have to overcome?
I think one of the challenges, and as I said, because our synthetic data is coming from this underlying digital twins, not all the teams around the world have people who can feed these digital twins. So, for example, if you're trying to train your quadruped in a desert environment, you have to create a digital twin of the quadruped. The desert itself, you have to make it grounded in reality. And not every time the teams have the skill set to make those digital twins. I think that's definitely one of the challenges we've had with customers in the past. And the ways we are solving that is through tools like GIS pipelines, which can allow you to just input longitude, latitude of a place, and you can get a digital twin of that whole environment with everything like trees, bushes, buildings, roads in that environment. But still, there's places where people struggle in making those digital twins. I think another good avenue is, by the way, Unreal Marketplace, where people can just go and get some of these really high quality assets. And that's really shows the power of this platform Falcon, because it's built on top of the Unreal engine. It can leverage those Unreal Marketplace assets readily.
Mm-hmm. Got it. Felipe, any other thoughts on that question?
Yeah, so similarly, I think the having that catalog of digital twins that have been verified, so making sure that they're verified is crucial. I think it's a little bit of a chicken and the egg problem where it's like the bigger your catalog is, the more you can sort of bring in and the more things that you can generate that you're confident on them being realistic. So it's really building that catalog and really building that range of things that you have access to is one of the big challenges, and it's something that I think Duality is key part of what we're working on. Like Gandharv mentioned, being able to provide tools to leverage to have a large catalog and to create a large indistinguishable a large catalog of digital twins that are indistinguishable, and being able to bring that in and provide some tools to make the process of going from digital twins to environment to scenarios as streamlined as possible. I think is definitely some of the things that we're working on that are also some of the hurdles with getting started with synthetic data and digital twins.
Got it. I see. And so it seems also if you're creating your own, having access at least to subject matter experts or really making sure that you're doing the work to understand what is foundational for the digital twins and scenarios you're creating. So that way that you're, again, using that intentionality part of the guys correctly. Very cool. We're going to take also some questions we're getting from our YouTube live chat. Sorry, we're going a little bit out of order here, but again, if we don't get to your question here, we will 100% answer it on Discord after this webinar. So one question we have here is, can we iteratively fine-tune the model by collecting a small subset of real-world data where the model performs poorly after training on synthetic data?
Yes, I think we definitely want to avoid models doing poorly on synthetic data. So that is, for the most part, a red flag for that our synthetic data, something's wrong with our synthetic data, and we have to take a look at the synthetic data. I think a very popular technique is that approach of first training on synthetic data and then and then training on real data and fine tuning on real data. And I think that definitely works really well. But at the same time, I think that has been a red flag of what are some of the issues with the synthetic data. And what we've seen is that that process works really well when the synthetic data is lacking some of those noise properties of the real world data. It's kind of like the model learns on a cartoonish synthetic data. So these are data that don't have real noise artifacts. So it learns generally a simple and easy understanding of what objects are. And then once it gets fine-tuned on real data, it's able to like expand that understanding to the real world data. But we really want to make sure that that the model has access to that that noise from the moment it trains with synthetic data. We want to make sure it's already learning those characteristics and doesn't need to fine tune on the real world data. And so what we've seen is that, like, yes, if you don't have some of those noise properties correctly captured, you have this tendency, and this process works very well. If you do have the noise data, what we've seen is that we train on synthetic data, and if we were to fine tune on the real data, it doesn't provide that that big of a benefit.
Mm-hmm. Got it. So in a way, just to recap a little bit, ultimately the first step is always go back to the source of your synthetic data and be like, got it. Okay. Makes sense. I mean, and it makes sense in that when you're working with synthetic data, that's a quicker and cheaper process to do than if you have to troubleshoot that in real world data, I'm assuming.
Yeah. Definitely.
Okay. Very cool. It looks like we're just about to hit our end of our session here. Want to thank all of you for joining us, and especially thanks to Felipe Mejia and Gandharv Mahajan for talking with us about this subject today. We really appreciate your guys' time and your expertise. And as mentioned before, if you really want to see this just in action, especially using these Cheerios examples that Felipe used throughout this presentation, check out the link in the description. You can try the Colab example directly in your browser and see for yourself how we think about this, how synthetic data like this works. Other than that, if you want to try Falcon for yourself today, there's the EDU link down there as well. You can sign up, make a free account, and explore it for whatever projects you want to use it for. Thank you again so much. Any questions we didn't get to, we 100% will answer. Those will be on our Discord. Again, follow the link that's in the description and in the live chat. And you can think of new questions. You can follow up. We're always on there. We'll always be there to answer more of those. Thank you again all so much, and we'll see you next time.
Thanks.
Thanks, everyone.